Hi everyone, my name is Yu Wang. I'm a PhD student at NYU Marl. I'm going to present Who Calls the Shots? Rethinking Future Learning for Audio. This work is collaborated with Nick Bryan, Justin Salomon, Mark Cartwright, and Juan Pablo Bello. Future Learning, FSL, is a machine learning technique that aims to train a model that can recognize a new class based on only few examples, known as the support set. This field has seen notable advances in recent years, especially in the image domain. Most of these works focus on a standard future learning setup, where the target problem is C-way K-shot classification, where the model aims to discriminate between C previously unseen classes with K examples of each. Standard future learning often focus on single-label multi-class problem, where each example has only one active class. And it usually assumes the support set has perfect examples, for instance, high-resolution images centered on the target objects. While standard future learning is commonly studied, many of these assumptions might not be practical when applying to real-world audio-specific problems. So in this work, we base our study on a different setup. First, we consider a few-shot continual learning problem, where the goal is to expand an existing audio classifier by adding a new class based on few examples. Next, we focus on multi-label scenario, which is a common scenario for audio since sound events can overlap in time. We also explore different support set properties to understand the impact of different use cases. For example, can a user provide examples with other overlapping sounds or with low signal-to-noise ratio? By performing experiments under this setup, we hope to gain audio-specific insights on FSL. The few-shot continual learning framework starts with a base audio classifier, which predicts class-wise likelihoods over a set of base classes that it was trained on. This classifier can be viewed as a combination of a feature extractor and the last classification layer. Then on top of that, the goal is to expand the output vocabulary with an unseen novel class by providing few examples. We run a series of experiments within this framework to see the relationships between several design choices and their impact to the model, including the feature extractor architecture, the few-shot method we use to learn a new class, and the support set selection criterion. To do so, we create a new dataset, FSD mixed clips, which has three properties that are hard to find altogether in an existing dataset. First, it is a large dataset consisting of over 600,000 of 1-second soundscapes. Second, we have perfect annotation because we programmatically mixed each clip using Scaper by sampling foreground sounds from the FSD 50K dataset and using Brownian noise as the background. We also have full control of the acoustic properties of each clip, specifically the level of polyphony, which is defined as the number of sound events existed in a clip, and the per-event signal-to-noise ratio. Also, this dataset will be freely available on Zenodo. To use it for few-shot continual learning experiments, we organize the dataset to get disjoint sets of base and novel classes, where the models are trained on base data only and evaluated on both base and novel classes. In the first experiment, we tried 3 different models as the feature extractor. They are all CNN-based with different number of trainable parameters ranging from about 500,000, 6 million to 80 million, representing different model capacities. We also experiment with using a pre-trained model as the feature extractor. The trained model predicts the test data in a joint label space, and we compute mean F measures across base and novel classes separately to further break down the performance. First, we see that base class performance increases with increasing model capacity. This fits our intuition that a deeper model performs better. However, this trend does not hold on novel classes. We see a trade-off between overfitting base classes and generalizing to novel classes. Besides training the feature extractors from scratch, we try using the pre-trained OpenL3 embedding model, which has the same architecture as our previous model with middle capacity, but is pre-trained on a huge amount of unlabeled videos via self-supervision. The results shows that the pre-trained OpenL3 model achieves the best novel performance and the most balanced performance between base and novel classes. We use it as the feature extractor for the following experiments. In the second experiment, we try 3 different few-shot methods to learn the novel class. In addition, We evaluate these methods with different number of support examples to understand the relationships between them. In the first method, we compute a prototype for the novel class by first embed each support examples using the base feature extractor, compute the average embedding, and treat it as a new classification vector. The classification layer in the base classifier can be viewed as a matrix where each row is a class-wise vector, where we multiply it with the extracted feature of an input to predict a class-wise likelihood. So by combining these base metrics with the new classification vector, we effectively increase the output vocabulary by 1. This approach serves as a simple baseline that relies solely on the feature extractor. Next, we try the dynamic few-shot learning method, DFSL, which not only computes a prototype embedding, but also apply an attention mechanism over the base classification matrix to exploit learned knowledge of the base classifier. This approach goes a step further and requires an additional training stage at train time. Lastly, we try to directly train a binary logistic regression model for the novel class based on the support set. This is a standard transfer learning approach. Some of the recent works in the image domain show that simple transfer learning can outperform meta-learning-based algorithms on few-shot learning problems. We want to see if this is also true in the audio domain. Note that we need additional negative examples to train a binary model, so we randomly sample a set of data from the base training set. Overall, this approach requires additional training and data storage at inference time. We evaluate all methods with the number of support examples ranging from 5 to 30, representing standard few-shot scenario to low data regime. First, we see that when we provide a support set with only 5 examples, DFSL achieves best performance on novel classes. However, if we have more than 10 examples, logistic regression starts to outperform DFSL. This shows the advantage of transfer learning approach when we have more and more support examples. We can formulate this finding into a set of design choices. If it is critical to minimize user labeling effort or runtime resources, using DFSL with a small support set would be a better choice. But if we can have the user to label more than 10 examples and we have enough runtime storage and computing power, we can go for the transfer learning approach. Lastly, we experiment with different audio characteristics of the support examples. We compared monophonic examples to polyphonic ones, as well as examples with high SNR versus which with low SNR. Here we show the results with 5 support examples, but we saw similar trends with different N. First, we see that for monophonic test data, providing monophonic support examples achieves better results. While for test data with high polyphony, providing polyphonic support examples performs better. So if we know test sample characteristics in advance, we should try to match those in the support set. We see the same trend in SNR experiment, where matching SNR levels between support and test data achieves better results. On the other hand, with polyphonic examples or examples with higher SNR, we can achieve more consistent performance across different test data. So if we don't have prior knowledge about the test data, choosing support examples with more complex acoustic characteristics could be a safer choice. This finding holds for both few-shot methods, DFSL and logistic regression. To recap, in this work, we perform a set of experiments under a few-shot continual learning framework for a multi-label audio classification problem, and summarize these insights we learned into audio-specific recipe. First, for feature extractor in the base classifier, we observed a trade-off between performance on base and novel classes, and show that the pre-trained OpenL3 achieves more balanced performance. Next, the choice of few-shot method depends on if we have limitation on labeling budget or runtime resources. If yes, DFSL with small support set is preferred. If not, logistic regression, the transfer learning approach with more support examples, would achieve better results. Lastly, to select support examples, if we have prior knowledge about the acoustic characteristics of test data, we should match those in the support set. Otherwise, we should choose examples with more complex characteristics. This recipe serves as a general guideline and can be tuned based on different application scenarios or desired user interaction. We released the code, the FSD mixed clips dataset, and an intermediate dataset, FSD mix set, which contains 10-second recordings. Please check out the GitHub repo for more detail. Thank you.